O próximo plenarista tem a honra de apresentar o professor Rahul Pandharipande, que estudou em Princeton, onde tirou o bacharelado em 1990, fez o doutorado em Harvard em 1994 e atualmente professor de Princeton. Poderia dizer a respeito do trabalho dele, entre outras coisas, que ele seguiu, em poucas palavras, do Attia, de pegar, ainda no século passado, um pedaço da matemática que está realmente sendo desenvolvida nesse século. Então, professor Rahul, que eu vou dizer em inglês, he also claims to be a good soccer player.
Oh, I don't know about that, about the soccer player, but anyway, thanks for the invitation. I'm very happy to be here. It's kind of an amazing city, Rio is. So I'm going to talk about modern enumerative geometry, and that's kind of far away, so I don't always put the slides there. So I wanted to give kind of a basic talk because the actual motivating questions are very, very elementary, almost naive. So if you look at let's see how this thing works. Okay, if you look at the beginning of the subject, it's not in focus at the top. Let's see. If you look at the beginning of the subject, so enumerative geometry, we're going to count objects in algebraic geometry. And certainly the very first problem everyone is extremely familiar with, which is the question of Euclid. How many lines pass through 2 points in the plane? And there's the answer, it's 1. So this is, in some sense, the beginning. And this is the kind of extremely naive question we're going to discuss today. Although we'll see that so over the course of history, the answers become more and more complicated. So let's see. So I don't think that merits putting up. So I will start with 2 classical examples. The first one is that of Hurwitz covers. So Hurwitz covers, and this is the questions from, I think, about 1890s, his papers, Hurwitz papers. And the picture here, I drew it for an algebraic geometer, for a topologist. And the idea is you study a surface. So here I write CP1, an algebraic geometer writes that as a straight line. And this is also the Riemann sphere, which is a sphere. And I pick points. So here I have 4 points, and I look at surfaces that lie over, that cover, that are ramified at these 4 points. So the formal definition here is in the bottom, for example. So this is the definition of the number, this Hurwitz number. It's the number of genus G degree D surfaces that cover CP1 with simple ramification over these red points. And this is given by the Riemann-Hurwitz formula, 2G minus 2 plus 2D branch points. So that's this number. And as I said, this is a picture here for degree 2, but it can be written in any degree. And this simple ramification just means that all the sheets, only 2 come together at this point. So this is this Hurwitz covering system. So this is a classical problem in enumerative geometry, how to enumerate surfaces covering the sphere. And if you read Hurwitz papers, also Hurwitz papers are in German, and it's hard to read for me. And one of the papers where he discusses how to solve this problem, if you look at the introduction, he describes how he's on a holiday in Switzerland and talking to a chess master. And so, I look at the dictionary and look at it very carefully, and it's actually true. He says that he was stuck in how to solve this problem. He went on holiday in Switzerland, and he met this chess master, Lasker, who was also a mathematician, and Lasker solved the problem for him. So that's so this is a very early problem in enumerative geometry. And just to give you an example, I'll give you a modern solution of this problem, how to count these numbers, which is not Hurwitz. I mean, there's very many ways to count these numbers related to representation theory, etc. But here's a modern way. It's a recent method that I had conjectured in '99, and Andrei Akunkov, my colleague, had found a solution for this in 2000. It says if I look at these Hurwitz numbers and I put them in a generating function, So here are these numbers for every g and d. I put them in a generating function with a parameter lambda for the genus and a y for the degree, and there's exponential factor. And if I look at this, the new function that's given by these coefficients, it actually satisfies a very nice equation. This is the equation. That's the equation. And if you're familiar with integral hierarchies, this is just the Todo equation. And in fact, so this solution is some kind of new perspective on these Hurwitz numbers. This does, in fact, the generating series. The generating series gives you a solution of this Todo equation. And in fact, this equation determines them all. So this is some kind of flavor. In fact, that's not the topic of my talk, so I'm not going to say much more about that. In the next dimension, if we instead of looking at problems of curves in mapping to P1, we can look at P2, and you get this problem of severity degrees. So it's the this severity degree problem. And this although it's called now the severity degree problem, it was studied by Schubert and Zeuthen also in the 19th century, about the same time, in fact, as these Hurwitz covering problems. And this is a more straightforward generalization of Euclid's question. Here I drew an example. We look at CP2, which is this green thing. And I put some points, these red points. There's 8 of them. And I can ask how many cubics pass through these 8 points. But I asked for the cubics to have one node. So how many one-nodal cubics pass through these points? In fact, there's 12 of them. I drew just one of them. There's 11 others. And so this problem of severities is that in here, how many plane curves, so these are plane algebraic plane curves, of genus G in degree D pass through this many points. So this is the, I would say this is somehow an analog of the Hurwitz problem. The Hurwitz problem is maps to P1. This is an analog of it for P2. And as I said, it's the most straightforward generalization of this Euclid question. How many? So this problem also people have been thinking off and on for a while, and there's very many ways by now to solve it also. They're all more complicated than the Hurwitz question. But again, just to start, I wanted to show the kind of flavor of what this subject is like. A solution in a particular case, more recent solution. So here I wrote the top here is number of solutions. It's a very problem. It's a genus and a degree. So if you look at this 0 and 1, that's how many genus 0 lines, degree 1 through 2 points. So that's this Euclid number of 1. This is also very well known, how many conics through 5 points. That's also 1. And this is the number that I had the slide, so I'll put that back up here. That's this 12 number here. The answer to this question here is this N03, how many cubics with one node pass through 8 points? It seems like a complicated question. The answer is 12. And as I said, there's very many ways to solve this problem. It's actually not such a hard problem to solve. Starting with Zivron's methods in the 80s and Kapras-O'Harris in the 90s, no answer is as simple as the Hurwitz solution. But I wanted to give, just to give an example of how these solutions look like. I wanted to give here the simplest one, maybe the prettiest example of this. So if you look in genus 0, that's here. If you look in this genus 0 case, there's a very nice solution available, and it's also in this language of generating series. So if I look at this generating series of all these genus 0 numbers, these are this genus 0 severity problem numbers, and I put one variable y for the degree and another variable y for, well, there's these two variables, y1 and y2, one for somehow the point conditions and one for the degree. And there's this factorial. And it turns out by this maybe somehow, again, more modern perspective, so this is this WDVV, which is Witten-Dickerhoff-Verlinde equations. And an application first noted by Kontsevich, this generating series also satisfies a differential equation. That's that. These are partial derivatives. So this generating series of these, this kind of naive enumerative question actually satisfies this partial differential equation. And together with the Euclid number, this actually determines them all also. which is an elementary to say. This is the beginning. I mean, both these examples are beginning of different subjects. The fact that the Hurwitz numbers give you a solution, the Todo equation relates to some integral hierarchies in that dimension. The fact that these Severi problems give you a solution to this equation is the beginning of another direction, which was noticed by Dubrovin in the study of Frobenius manifolds in relation to singularity theory. Both those things are not the topic of my talk today. So this is somehow background on counting problems in algebraic geometry in dimensions 1 and 2. All right, so maybe I'll leave that solution. So what I really want to talk about is counting in dimension 3. So this is really the topic of my talk, counting in dimension 3. So neither of these these topics in 1 and 2 are the topic of my talk. Both are classical questions. If you look at this Hurwitz problem, the Severi problem, they're kind of extremely naive classical questions. You just look at some kind of elementary geometry and ask how many solutions you can count. And as I view that as a good thing about the problems, that they're completely naive. You can pose them completely naively. The fact that their answers have this kind of rich mathematics related to maybe perhaps unexpected directions shows that even these naive questions are actually central in mathematics. And here, I say there's kind of this investigation in dimensions 1 and 2 is, I'd consider, classical enumerative geometry. And what I mean by that is you start with some well-defined enumerative problem and you solve it. This is this kind of classical approach. You think, okay, what is this problem? I identify it, and I work on it, and I solve it, and I get the answer. So this is not what I consider modern enumerative geometry, which is rather, it happens the other way around. So here, I'll put this slide. So what I consider really modern enumerative geometry is rather the other way around. So here it is. In modern enumerative geometry, you start with the answer and you try to discover what's being counted. Okay, and this is, and you might laugh, but this is actually how the subject goes. So I'll explain this perspective, this enumerative geometry in dimension 3. All right, so this is really what I want to talk about today. So the problem with counting in dimension 3, we'll see, is it's not a naive question. That's a different from the past. It's really not a naive question. And I want to now discuss a little bit about this. So the simplest dimension 3 space, of course, is CP3, which is, I just think about a space. And certainly curves in CP3 have been studied since, well, for a long, long time. And certainly there were treatises written by Noether and Halfin. That was already 100 years ago, more than 100 years ago. And this idea is that, okay, plane curves are simple. We can study around this Hurwitz problem and understand it very simply. What about curves in space? After all, we live in three-dimensional space. What about families of curves in space? So these are algebraic curves in space. So again, you can start by asking some kind of naive questions. What does the family of genus G degree D space curves look like? So that seems like a good question, especially since the answers were relatively straightforward, well, in earlier dimensions. And unfortunately here, one discovers quickly this is a hard problem. So the answer about what families of space curves are, dimension 3, this is also almost impossibly bad. It's hard to predict when these families are non-empty. It's not known how to find their dimension. They can be very singular. They can have nilpotence. I mean, in some sense, philosophy advanced by Mumford, saying really they can be arbitrarily bad things. The spaces of families of space curves have, on the face of it, no redeeming geometric properties. They can just be as bad spaces as possible. So then the situation seems unfavorable to some kind of naive enumerative geometry. Like how can you think about a enumerative geometry when the actual families of these space curves are so terrible? And this is why it's not a classical subject. If you look 100 years ago to the people who were counting, Schubert, Zeuthen, they were not counting arbitrary genus curves in space because it didn't make any sense. But nevertheless, we would like to take this kind of naive point of view. We would like to ask, so the blue are some conditions. So this black thing is CP3. And we'd like to put some lines and some points, these blue conditions, and just ask how many space curves of genus G in degree D meet this given configuration of lines and points. There's a problem with, I think maybe I'm using A4 paper here. Lines and points. So as I said, the important thing to understand here is not you want to approach the subject naively, just ask this kind of naive question that was asked in the earlier dimensions. But there's also understanding that you cannot proceed this way. I mean, this question makes no sense. You don't know how many dimensions to put. You don't know. So this question does not make sense. So, of course, also we can consider arbitrary threefolds. I mean, why just projective space? It's not necessary. And in fact, if you look at this case, which is very popular nowadays because of closer connections to string theory, you can consider arbitrary threefolds, in particular this Calabi when X is Calabi Yau, which is to say that its canonical bundle is trivial. This is a very interesting case. And one has the same philosophical questions. You want to understand some kind of naive counting problem, but it just doesn't make any sense. So even to define the problem, you need some very new ideas are required. Because this has to do with the fact these families are terrible. And in fact, this can be overcome. And the thing that may be surprising is that there's many different ways to overcome the problem. So in fact, I'm going to explain this talk, there's 3 different ways to proceed here. At least 3 different, and probably more in the future. And these are very different ways, and one can wonder, how can it be? It's a kind of a naive problem to start with. How can there be so many different ways to proceed? So this is what I want to explain a little bit about. So the three approaches I will discuss. So the first one, so this is maybe like one per decade. So the first one for roots in the late 80s is the Gromov-Witten theory, and this requires this moduli of maps. It says that, okay, we're going to look at a counting problem. Instead of looking at these curves inside the space, let's look at maps, and try to proceed from there. And this has roots in topological string theory and Gromov's work in symplectic geometry. And this is one way to proceed, and I'll discuss it. The second came maybe about 10 years later in Richard Thomas's thesis, which is this Donaldson-Thomas theory, which says, okay, let's look at a curve. A curve is really a subscheme. It gives me an ideal sheaf. I can look at moduli of sheaves and try to understand how to regularize that problem. The most recent approach I've been working on with Richard Thomas, and maybe in this past year, is yet another idea, which just says that if we look at a curve, you can have a curve with a section that gives you a complex in the derived category, and you can study moduli of complexes in the derived category. This is kind of yet another approach. And these things are, in some sense, quite unrelated to each other. If we look at maps or sheaves or objects in the derived category. And so as I said, the geometry behind them are all very different, but then there's this kind of miracle that occurs, and that's kind of the main point of this talk. I want to say that they all arrive at the same definition correctly, at least conjecturally, of this naive question of counting in dimension 3. That these these three independent approaches will lead to the same numbers. And I think that one can say, make some kind of meta conjecture that, in fact, that that the counting problem that's going to be defined from these three approaches is probably the counting problem that will be arrived by any reasonable regularization of this problem. And these three different approaches are connected to kind of three different directions in mathematics. I'll try to say that. This Gromov-Witten theory in maps, if you look at the case of space curves, this is related, to understand this is related to the geometry of the modular space of curves, and it's kind of Witten-Kontsevich work, matrix models, and things like this. This Donaldson-Thomas theory is completely in a different direction, and it's related to more commutative algebra constructions, box counting, theory of random surfaces that Andre and Rick Kenyon have worked on. It's really a completely different direction. And this last direction here in derived categories is there's some kind of there's some kind of amazing thing about derived categories. Derived categories arise. They came up in Verdier's thesis and work of Grothendieck to explain. These are like a language for cohomology theories. And what's happened, and it sat like that for a number of years. What's happened recently in the last 10 years, in both this homological mirror symmetry program and algebraic geometry, it's understood the derived categories are, it actually turns out to be the exact right, and this happens with Grothendieck, anything he touches turns to gold, but it turns out there's exactly the right language, and one should study them, take them very seriously, and study them in their own right, the derived categories. And this kind of thing happens all the time in mathematics, but it's always a surprise when it does. So this is it's really saying the geometry of the derived category comes in here. All right, so I want to just briefly explain the three spaces behind these approaches. So the first is, the paper is too long here. So the first is the Gromov-Witten theory. And so as I said, the background of this is we're going to try to find some regularized counting in dimension 3. And there's going to be three different approaches. And the first one I want to explain is Gromov-Witten theory. And here, the basis is this moduli space of stable maps. So what is this moduli space? We look at maps, and here I draw a curve as a topologist. So here I look at a map from a genus G curve to F. This map is algebraic, so this is actually a curve, which means it's or you could think of it as a Riemann surface, and this map is analytic. That's fine also. And it has a genus, that's a genus there, and it represents some class in H2, the fundamental class, and that's the beta. Those are the two discrete invariants. And this moduli space it's compact, which is why there's this bar on top. And to be compact, you have to allow some degenerations. And the clever idea, which has been somehow used repeatedly in the subject, and it was exploited here by Kontsevich, is that you only allow nodal degenerations. You don't care much about this map, but just allow that the curve can have a node. It's a degeneration. These objects also lie in the moduli space. And it turns out if you do that, this moduli space, bottom here, this is a compact algebraic variety, or it's a stack, but anyway. So this is, if we view X as our threefold, this says that if it's space, a projective space, CP3, then this is just some degree, and it says that if I fix the genus in degree, I get some compact algebraic variety actually parameterizing these maps. And I would like to use that in some way to address this counting problem. This is like the first step. So the second one I explained, the second approach is this Donaldson-Thomas theory. And as I said, this is the topic. This theory was developed in Richard Thomas's thesis, PhD thesis, which is like 96 or 97 or something like that. So here, instead of taking the moduli space of maps, as I said, that you can look at a curve as a subvariety or a subscheme. And then it's a well-known, for a long time also, in Grothendieck in the 60s is that one knows how to parameterize subschemes of algebraic variety. It's parameterized by the so-called Hilbert scheme. It just parameterizes them all. And here I tried to draw a picture of one. So here's a subscheme. It could be on a curve, and it had some non-reduced structure. It's a fat curve. It could be a fat singular curve. It could have some points and fat points. Anyway, given a subscheme, you get an ideal sheaf. Here's X. There's a subscheme. You get an ideal sheaf. And this Hilbert scheme can be thought of as parameterizing these ideal sheaves. So it parameterizes these ideal sheaves. And if you look at this, if you look at the indices, n is supposed to, I don't know if I can fit them on. Oh, they're on the bottom. So if you look at the indices, n is the holomorphic Euler characteristic of the subscheme, and beta is the class represented by the subscheme. It just comes from the curves. So this is in some sense kind of an old idea that you should parameterize curves and threefolds by the Hilbert scheme. I mean, maybe if you have or have not seen this kind of stuff before, the twist here is to view this Hilbert scheme as parameterizing ideal sheaves. That's really it. So it's viewed as the moduli space of sheaves, not a moduli space of subobjects. And the last one, as I said here, is as complexes. So this is complexes, which I've been working with Richard Thomas, and we call this P because Le Potier actually had studied these. And in some sense, he had studied some aspects of these before. So if you look at this space, it's a moduli space of complexes. And this idea of studying a moduli space of complexes in the derived category, I mean, that's kind of a strange idea. And it's, I mean, I would say that people have only started thinking about such things in the last few years. And it's due to work of Bridgeland on stability, and Inabi and Lieblich have been trying to develop some kind of foundational theory for it. I mean, in some sense, well, I mean, algebraic geometry has been kind of fortunate, since if you wanted to look at moduli spaces of any kind of object in algebraic geometry, you really didn't have to do very much work at all because of the foundations laid by Grothendieck and Mumford in geometric invariant theory. And those guys did such an amazing job of laying the foundation of the subject that really not much work had to be done at all to apply it in various ways for, I don't know, it's been 30 years or something like that. But now if you come to this, if you look at this problem of moduli spaces of complexes in the derived category, this is maybe like, for the subject, one of the first has to confront these kind of foundational issues that were not addressed by Grothendieck and Mumford. This is being, so there's been some development of this now. And this is the kind of moduli problem that does not fit in the foundations. But it's in one way the subject is definitely going to go, because it's an incredibly natural way to look at it. So you look at complexes, and you want to look at moduli of complexes, which means a complex. Well, so the idea we'd like a moduli space of pairs. We have a curve and a divisor. So here's a threefold, there's a curve, and there's a divisor. So why do I call this a complex? Because that's a very naive, this kind of geometry I've described is kind of naive. So why do I call that a complex? And well, I call it a complex because of the following reason. If I have a divisor, I get a line bundle, which is just the functions with poles on that divisor. But I don't just get a line bundle, I get a section also. So given a curve and a divisor, I get a line bundle on the curve and a section. So here I try to draw a curve and a line bundle on the curve. So given this data of a curve and a divisor, I view this as actually a complex, where this is O on the threefold, and this is a sheaf supported on the curve. So it's a complex, but I view it as complex in the derived category. And as I said, if you've never thought about the derived category, one thing about it, it's an extremely slippery object because you can write down a complex, but the complex is deemed to be equal to everybody's quasi-isomorphic to it. And I said, it's kind of a slippery thing. And one would like, when to define the space, is to parameterize all complexes of this form and parameterize them up to quasi-isomorphism, where n is the Euler characteristic and beta is the class of this sheaf. So, as I said, for this, if we review where we are here, if we have a threefold, and as I said, I want us to address this kind of naive counting. And so this idea of addressing this naive counting is first find some space which parameterizes the objects I want to count, then maybe put some conditions so it gets finitely many objects. And to start, I have a proposal now of 3 different spaces. One is the space of stable maps. The second is this Hilbert scheme. And the third is this moduli of pairs in the derived category. And these are, I should say that this moduli of pairs, in general, it's very hard to construct these moduli spaces of objects in the derived category and even their foundational issues. But in this particular case, one can really do it. So these are 3 really different spaces that you could associate to a threefold. And they all, in some sense, parameterize objects that look like curves, but they parameterize them in 3 different ways. And so you could say, okay, how does this help with enumerative geometry, my naive counting problem? So the idea is maybe we should be counting, you could be counting this guys, you could be counting objects in the Hilbert scheme, you could be counting pairs in the derived category. Does this help? And the answer is, well, not really yet. It doesn't help. And the reason is because, as expected, all of these moduli spaces are very badly behaved, just because that's what I said at the very beginning, that any parameter space of curves in threefolds is bound to be very badly behaved. So all of these are extremely badly behaved in all respects. So in that long list of respects that you don't know what their dimensions are, whether they're non-empty, whether their singularity is all horrible. But they have one redeeming feature. These 3 problems, which is why their definitions are chosen very delicately. They have 3. These 3 have They all have the same redeeming property, which is that they all have a good deformation theory. And this is really the crucial point, that they have that all 3 of them had a good deformation theory. And in the sense that, it looks like if you've never seen this and you watch this talk and I'm writing down these random moduli problems, you might think, well, why do I write those random moduli? Why can't I write any other ones? And there's very few that have a very good deformation theory. And in some sense, you'd be lucky when you studied this problem at the beginning to find one that had a good deformation theory. And here we have 3, which is maybe unlucky because then you think, well, how? So about the deformation theory. So the best deformation theories, and this is now some kind of conceptual discussion that's only somehow related to the talk and the fact that we need to apply it. But there's a kind of conceptual discussion of deformation theory. So deformation theory tells you, if you have an object, how to move it infinitesimally. And the best deformation theories in algebraic geometry are controlled by 2 groups. There's the deformation group, which is the tangent space to moduli, which really tells you how to move. And there's the obstruction group, which in some sense tells you which way you can't move. So this is this topic of deformation theory in algebraic geometry, and there can be very complicated deformation problems, which are controlled by more than 2 groups, which are obstructions, substructions, higher obstructions. And in fact, a typical problem in algebraic geometry will be controlled by many more than 2 groups. But the best problems are just controlled by a deformation group and obstruction group, which tells you. Yeah. And it turns out, and which is in fact why I've discussed them and why they were introduced by the various people who introduced them, is that these guys all three of these spaces are very, very special. All three of them have these two-term deformation theories. And the fact that they do is, well, if you look at this case of maps, is extremely well known. It's just the fact that if you have a curve mapping to f, say it's a fixed domain for simplicity, how do I decide how to deform this curve, this map, infinitesimally? This is such a simple idea that one can say. If I have a curve, so here's x, and I have this curve mapping to x, so let's just draw it here. It's curve, and I want to move this map. Well, how am I going to do it? Well, I take this, so here's my curve. How do I decide how to move this map infinitesimally? Well, at every point here, that's this point here, there's the tangent space of x, and I just tell how to move it, how it's going to move in that direction. So that gives me this way of how to move it. This infinitesimal moving of this curve is nothing other than this section of the tangent bundle. So this is kind of a simple idea, and it's true. And then what's not so simple, more subtle, is that the obstruction theory is given by just h1 of this tangent bundle. And then what you can imagine is that I mean, this is not a proof, but you can imagine that these are the only two things that are going to control the deformation theory, simply because a curve doesn't have any higher cohomology. And this would be a correct deduction, although not rigorous. So here we're very fortunate, and it happens that it's governed by these two groups, a deformation and obstruction group. Now, what about these other moduli spaces? Let's look at the Hilbert scheme. So now the issue is already less naive, because you have to understand deformation theory of sheaves, which is a much more delicate matter in some sense. And so look at this Hilbert scheme. We have an object in this Hilbert scheme is given by an ideal sheaf. And so the question is, well, how do I deform sheaves? Or how do I deform bundles, these kind of bundle objects? And the answer is it's an xed. It's this xed 1 II. So this is this is the global x of these sheaves, and this is a vector space, and it tells you how to deform it. And I put a 0 here because I want this to be traceless, but maybe we forget that. So, and the obstruction space is this x2. So this is also a pretty well-known deformation theory of sheaves. But then you might say, what about this x3? It's a threefold after all. There could be an x3, and there could be higher obstruction. But x3 turns out to be 0. So what happens in this threefold case is this x3 and x0 are both 0. The traceless parts they're both 0. And this kind of argument is already special at dimension 3. So here it turns out that this ideal sheaf theory is actually governed by two groups. Deformation obstruction group, and again we're happy. And this observation, as I said, was the observation of Richard Thomas's thesis. And then finally, the third space. What about these pairs in the derived category? What's their deformation theory? And this is where really viewing them in the derived category is crucial. And maybe I'll just make this point because it's. So we take this pair. It gives us a complex in the derived category. And you can say, well, what is the deformation theory of a complex in the derived category? This is different than deforming just these sheaves, because you have to deform these sheaves, and then you have to mod out by quasi-isomorphism. So the question is, what is the deformation theory of complex in the derived category? And the answer, and this is what's great about the derived category, is it's a complicated object, but it's built, and this is this idea of growth and deconvertier, to objects in the derived category. There's a difficulty in the derived category. It's the slipperiness of quasi-isomorphism. But once you overcome that, formally they behave just like single vector bundles. And that's the idea of the derived category. So it turns out here that if I have this complex, one can consider x in the derived category between two complexes. And this deformation theory is just x1 of these two complexes in the derived category. And the obstruction theory is x2. And again, you can prove that the other two terms are 0. So But it's crucial here to look at this thing as an object in the derived category. If you look at them as actual maps of sheaves, then the deformation theory is different and not governed by two objects and basically a nightmare. So this is the... Okay, so if we look at this deformation theory, the principle, which is this theory of the virtual class, says that if you have, well, roughly speaking, what this discussion of the virtual class is, if you have a deformation theory that's governed by two terms, you get a virtual class. So this is first proposed by Jun Li and Gang Tian, and also in algebraic geometry, Baron and Fantecchi. And it's just, in some sense, this philosophy can be summarized in that way. If you have a moduli problem, and by some kind of fortunate occurrence that its deformation theory is governed really by just two groups. There's a deformation and an obstruction theory, an obstruction group. If you're so lucky that that is the case, then in fact, the moduli spaces carry a virtual class. And this fixes very many of the conceptual problems. So what is this virtual class? It's so since all three of our spaces, I argued, have this two-term deformation theory, they all carry this virtual class. And the virtual class is a homology class. In fact, it's an algebraic cycle class. But anyway, it's a homology class, and it has an expected dimension. And it sits in these moduli spaces. So it's just a homology class. And the expected dimension turns out to be twice the twice, because you're jumping back and forth between real indexing and complex indexing, twice the difference of the deformation space and the obstruction space. That's the dimension. And it turns out in all three of these cases, and this is the first indication that something lucky is going to happen, is that in all three of these cases, if you calculate what the difference between the deformation space and the obstruction space, so in the case of the maps, that was given by some cohomology of the tangent bundle. In the case of the sheaves, that was given by the X. In the case of the complexes, that was given by the hyper-X. You calculate them, you get the same answer. I should have put the 2 there too. But the difference here is this. Okay, maybe I'll put it. The difference is 2 times the integral of the first Chern class of X along the beta, which was what, so I can say that more in more elementary terms here, is that if you have a homology class, the Chern class is a cohomology class, then you can pair the homology and cohomology class to get a number, which I write as an integral. You can write it however you want. So this is the first indication that something nice is going to happen, that these three different moduli problems, they all have the same virtual dimension, that the differences between the deformation and obstruction theory is the same number. So I wanted to say a little bit about this virtual class, because it's it's an extremely nice idea, and in some sense, if one wants to say, I said this enumerative geometry of threefold is not a naive question, and the ideas involved in just the definition are somehow, one can be said in a very simple way. There's 3. 1 is find the right moduli space. 2, show it has this two-term deformation theory. And 3, proceed to construct its virtual class. So I tried to draw a picture of this virtual class. Okay, so this is the idea of the virtual class. You have a moduli space M. And if the moduli space has this two-term deformation theory, so there's the moduli space. That's that big blue lake here. And the idea is that the moduli space lives, in some sense, in the deformation space, and it's cut out by a section. That's this black is the section of an obstruction bundle. So it just happens usually that when you cut out this moduli space, this section of the obstruction bundle, it's something very bad. It can be very singular. If you look at a zero locus of a function, it can be very bad. But by perturbation, one can hope to move this black section around, and so then it cuts it transversely. And when you cut it transversely, you have a nice, smooth moduli space of expected dimension. And so this is the idea of the virtual class. And it's kind of a very simple idea. But what one needs to do in these problems is you need to find. So in general, you can't achieve. In algebraic geometry, really, you can never do this perturbation. You can't achieve such a good perturbation. But and this idea of this theory of the virtual class is that, but the deformation theory tells us what the class would be if there was a perturbation. That's the point, and that's kind of the main point. And it does it in all these cases. How am I doing? Oh, pretty well. So that's the picture. So if you take this lake and you perturb it, you get this nice river. That's that. And in some sense, the reason why these questions of enumerative geometry of threefolds could not be addressed 100 years ago is because this understanding was not there. And even somehow philosophically, you could say, I mean, maybe it's worth saying this. You could say, why is it that we're so lucky in these cases that really one can do this? And there are other reasons. And in some sense, in these theories that I'm talking about, these three of them, they all have path integral motivations, and you can view that this path integral is some ill-defined object in mathematics. But nevertheless, there is some kind of calculus about how to address it, and I don't think it's unfair to say that in these examples that this virtual class can be viewed as some kind of shadow of the path integral in algebraic geometry. I think that's relatively fair to say. That, meaning that there is already some kind of heuristic view about these type of integrals should admit regularizations, and this particular technique in algebraic geometry is telling you how to do it in algebraic geometry. Okay. So now, given these three moduli spaces and their deformation theories and the virtual class, it's now pretty easy business to actually define this enumerative geometry. So I tried to write this notation. So you fix these incidence. You fix these incidence conditions. Sorry. You fix some incidence conditions in X. So X is this threefold. So the incidence conditions could be you want your curve to pass through some points, maybe incidence to some curves, maybe pass through some surfaces. So you get some tuple of incidence. This gamma, I just want to say, is just the tuple of incidence conditions. It just tells me which points, which curves, which surfaces. And of course, I want to pick them generally. And I get now to define an enumerative invariance. These are just enumerative counts. I want to count stable maps that pass through these things. I could count stable maps that pass through these things. I can count ideal sheaves. I can count complexes in the derived category that are incident to these things. And so one has to think about how to make this. But this is all it's all straightforward once you have the virtual class. And roughly speaking, why it's straightforward. It's the following. So why it's straightforward is that so in each of these theories, we can now proceed without any problem. And why is it straightforward? So generally speaking, you have to decide, for a enumerative problem, you have to decide how many conditions you're going to put on. That's a reasonable question. And that is told to you by the virtual dimension. And it's this virtual class has a certain dimension that tells you how many conditions. So that's one of our original problems. We worried about the dimension of the moduli space, etc. This has been solved by the virtual class. There's a well-defined virtual dimension, and it tells you how many conditions to put on. The second is once you have these conditions, you want to somehow get a number out of it. And this is easy to do now here. And I just did it kind of schematically because otherwise one has to unpack a lot of notation for no reason. But schematically, the reason is that this virtual class is a homology class. And it's born as a homology class. And these incidence conditions, they're really, if you think about it, they're really cohomology classes. In Gromov-Witten theory, they're really cohomology class on the target. In these sheaf theories, they come from Chern characters of bundles. But anyway, they're really cohomology classes. And the one thing we can do is we can pair homology with cohomology, and you get a number. And that's this is somehow the reason why the virtual class really solves conceptually this problem. Okay, so here we have it. So now, if you follow this path I'm going on, we'll look at, I want to have some kind of counting problem for space curves. And not only do we have one, we have three. You could be looking at the way you count maps, way you count sheaves, way you count complexes. And yeah, so that's a little strange. So then you could ask, are these related? And in fact, that's what I wanted to argue at the very beginning, that in fact these are all, not only they're related, they're all the same. But they're the same after transformation. So if we want to make progress now, we're going to look at these generating series. And this is somehow, and it's part of the reason why I tried to explain the solutions, kind of more modern solutions of the enumerative questions in dimension 1 and 2, because the nice answers are all in terms of generating series. These generating series, in their physical theories, you're supposed to actually view these as actual partition functions of the theories. So in some sense, it's not unnatural. In fact, it's very natural to think of them as actual generating functions. All right, so we look at these generating functions. One for Gromov-Witten theory, one for the ideal sheaves, one for the pairs in the derived category. And they're just the most naive way you can think of a generating function. So you fix the class. The class is not moving. That's the degree. Just fix it forever. But what is moving is the genus here. If you fix a degree, you can look at all the genera. This is sum over everybody. And you put a genus parameter. This is just like I did in some sense for the Hurwitz number. And if I look at the ideal sheaves, I fix the class and I sum over the holomorphic Euler characteristic, every single one of them. And same for the pairs. I can fix the class and I sum over the holomorphic Euler characteristic. And you might think, well, why did I use U here and Q for these two? That's a good question. I will make one small point, is that this kind of... Oh, no, I won't. All right, so at this point in the talk, I said that one should believe that these three series are they're rigorously determined, and that each one of them is some kind of proposal for enumerative geometry of a threefold, three modern proposals. And so, yeah, so the conjectures are the slide that they're all equivalent, but they're not equivalent in a completely trivial way. So here are the conjectures. So all three are equivalent. I'd like to make some kind of meta-conjectures. Any reasonable approach to enumerative geometry threefold gives the same answer. So these three are equivalent. These are the three generating series. And you see they're not completely trivial equivalent. The first one was a conjecture that I made with Devesh Malik and Nikita Nekrasov and Andrei Akunkov. This is from like 2000. This conjecture, I think, is from 2003, maybe 4, I don't know. And this conjecture says that if you take this Gromov-Witten series in this variable u, and if you want to relate it to the ideal sheaves, you do something very funny. You take this ideal sheaves, you divide by the degree 0 part, and then you do this change of variables where minus q equals e to the iu, which is transcendental change of variables. So this is a very peculiar thing to say. I mean, it says that if you ask what this says, it turns so. First, you could say, can you really make this change of variables? It's an illegal change of variables because it starts with 1. E starts with 1. And you're not allowed. And like we teach our students, you're not allowed to make this change of variables because that requires convergence. So really one has to address this conjecture and say, well, yeah, in fact, not only are these things convergent, they're all rational functions in Q. That's part of the conjecture. So in fact, every three of these things in terms of Q, they're actually rational functions. This change of variables is legal. And how you should think about the difference between these two theories, is that really they're the same functions, that they're just taking power series developments around different points. And somehow one's analytic continuation of the other. It's these two. This was the conjecture from 2003. The more recent one with the derived categories As you can say, well, derived categories are more complicated, and it's a really headache to think about hyperx, and it's all that is true, so why do it? Well, you get a much nicer thing here. You don't have to divide out. It's just actually straight that this Gromov-Witten theory is just exactly this, the generating series in the derived category. There's none of this funny dividing out. And yeah, so it's, again, this guy's a rational function. So I would like to say one moment about that. So this subject is some kind of more or less new subject. And these conjectures, I've written them as conjectures. They're proven. We've proven them in various cases, especially with work with one of our postdocs, Alexei Oblomkov. So all of us and Alexei Oblomkov also, we proved this in many cases, like the toric case and things. I don't want to emphasize in the particular cases we've proven, because that's rather technical development. But one should view this really as a conjecture, saying these guys, really, these three different approaches give the same theory. And the fact they're related in a slightly peculiar way is saying that somehow these different theories are analytic continuations of each other, not completely straightforwardly related. I would like to say another point here, because it's so the conjecture also, which I didn't write, is that in fact these three functions are all equal. In fact, they're rational functions in Q. And we know a fair amount about these rational functions in Q also. In fact, they have poles only at roots of unity. And if you're an algebraic geometer and you find a geometric rational function that has poles only at roots of unity, you immediately think about zeta functions and the Weil conjectures. And there must be some kind of connection to actual characteristic P counting in this story that hasn't been made also. My feeling is if one could make some enumerative geometry of characteristic P counting, that one would also find the same answers, and there'd be some kind of zeta function connection for this. So let's see. So as I said, it's been proven. Let's see. I did have a slide about this proven, which is this part is certainly true. So we had proven it. I think last summer we had proven these two are equal for CP3 and other toric varieties. The theory with Richard Thomas is more recent, and we've only proven that in the toric Calabi-Yau case. And these proofs are really complicated and really not really fit for public display. So I'm not going to say anything about those proofs. They're really incredibly complicated. That all sorts of twists and stuff. I don't like them very much, the proofs. But as I said, especially since I believe this stuff is true for every threefold, proving the toric case is not so a big deal. Okay, so this is maybe the last slide. This is a more philosophical slide about what this is going on. So as I said, I started this talk with explaining this enumerative geometry in 1 and 2 dimensions, and those are completely naive problems in the sense that you can just explain them to a first-year student. This is the counting we're doing. Enumerative geometry threefold is not naive, and it requires this machinery just to make a precise problem. But on the other hand, once you're finished with that, just like in 1 and 2 dimensions with these connections, in 3 dimensions, in some sense, I didn't say this, but I should have said it before. From kind of aesthetic reasons, counting in dimension 3 is like the most perfect problem. And I didn't say this at the beginning. I should have. It's because there was a slide a long time ago when I explained what let's put it over here. I should have said this. That if I look at the dimension of this deformation minus the dimension of the obstruction space, that this is equal to this formula. It's kind of a surprising formula. I said this is supposed to be true for all these spaces. This is for X to the threefold. For this guy, and also the Hilbert scheme, and also the pairs. And you see, this formula doesn't depend on n here. So no dependence on n. And no dependence on g here. Just dependence on the degree. This is why I say it's the threefold is kind of most perfect. It's like this democratic counting problem. It just counts everybody. There's it's not biased at all the genus or n. And if you really think about this kind of aesthetics, the most perfect of them all is the so-called Calabi-Yau case. The Calabi-Yau case is when this is 0. Calabi-Yau is in this class, geometrically you make this class 0. Then everybody is, and this is completely democratic. Just count everybody the same. So in this way, the threefold counting is somehow aesthetically the most perfect counting problems in algebraic geometry. And then one sees that once one has these theories of counting in threefolds, that's an incredibly rich connection. So I tried to say this at the beginning, that if you go on the Gromov, so there's 3 roots here. If you go on the Gromov-Witten theory route, you immediately get the problems of moduli of curves, the intersection theory of moduli of curves, matrix models, integral systems. This entire Witten-Kontsevich story appears as, in fact, really kind of a small aspect of what's going on here. And we've used this to prove things. And, if you go via ideal sheaves in the Hilbert scheme, you get this connection to moduli of sheaves, and if you look at fixed point methods there, you get box counting and the theory of random surfaces, which was worked out by Andre and Reshetikhin and Kenyon, Rick Kenyon. And so again, it's something that one would think is completely unrelated. For example, the geometry of MG. But in fact, you find here it's not only related, it's almost exactly the same thing. And this most recent arrow is from this enumerative geometry threefolds and the moduli of complexes. And here, this is a much more recent arrow. I said Richard and I were working this out this past year. And here, what comes in immediately is questions of derived category stability, the Bridgeland stability, derived geometry, and this also gets grouped into the same, somehow the same place. So all these things are related to integrals of moduli of curves and random surface theory. And as I said, I view this more or less at the beginning of this kind of investigation. So I think that's the end.
Questions?
So would this series satisfy differential equations?
Yeah, so that's a different question about how to compute these series. And so, not as simple as the equations that I wrote down for 1 and 2. But they do. They satisfy very rich things. If you look at this series, like if you look at this series here, I could look at just the genus 0 part. And if I do that, say for the quintic, then that's related to the Picard-Fuchs, the mirror transform. This is, they're actually mirror transforms of hypergeometric series. So that's certainly true there. And that's believed to be true in all genus for the quintic. This kind of generalization of that. For projective space, they satisfy different types of equations, these Virasoro type equations. But, yeah, it depends on the ambient space. Yeah, that's right.
More questions? So let's